Hello, Honors Algebra 2 Trig. This is Mr. Ahrens, and we are doing notes right now on function notation. First of all, I want you to understand that there's these two different ideas. One's a relation and one's a function. And a relation is a mapping. Oh, I'm going to try to change the thickness on these. Make sure you're patient. This is a mapping of points between two variables. For example, if you had the numbers, say 3, 3, 4, 5, 8, 7, 8, 11, this is a mapping of different x values compared to certain y values. It's saying that 3 could become 3, that 4 could become 5, and that 8 could become either 7 or it could become 11. Relations don't necessarily have to have the same number of input values or outcomes. They're just a way that a set of numbers is mapped. Now, a function is specifically a relation where every input has a specific outcome. That's one specific outcome. In other words, when you pick a input, you know exactly what outcome it's going to go to. In the first relation that we have here, this is not a function because when you choose 8, you don't know whether it's going to turn into 7 or whether it's going to turn into 11. Functions are very predictable. When you put something in, you'd be able to define exactly what is going to be coming out of it. Now, if we look at these functions here, or these relations here, they're all mapping sets of points. For example, this here maps the point 1 to 8. So when there's an input of 1, there's an outcome of 8. There's infinitely many points plotted here, so there's infinitely many points in this relation. Our job is to figure out whether it's a function or not. In this case, it would not be a function because when you input 1, you're not sure if you get an outcome of 8 or if you get an outcome of -2. So we have one input with two different outcomes. It's not a specific known outcome, therefore it's not a function. Oftentimes, graphically, people refer to having the vertical line test. And what that means is that a single x value should only have one point on that specific x value to be a function. And in this case, since there's 2 points on all of these graphs at a single x value, that would describe it as not a function. The second one here is a function because for every specific input, you only have one outcome. So when you look at it, if you pick any input, there's only one outcome from it. So we look here at this input, this is the only outcome here at 1. When you look at this input, there's only one outcome here at 5. So every input has specifically one outcome. Right here in the third image, we have a piecewise, but so it changes patterns partway through. But this is still a function. And it is a function once again because every single input only has one outcome, as opposed to the sideways absolute value graph in the first picture that has 2 outcomes for one specific input. When we look at these 2 equations down here, refer to this as equation A and equation B, what we would need to know is that if a single input x, if every input x has a single outcome y, or if it could have multiple. In this case, this polynomial function in A is a function because every value you substitute in, you're going to only have one outcome value. So if you input x being 1, it would be 1 plus 3 plus 1. It would be specifically a y of 5. It's not that you're uncertain which y value you get. You will always get 5. The same with any value that you substitute in. Whereas in B, if I input x being 1, I would get, this is a bad example, I'm not going to choose 1. If I made x being 7, I would have 7 minus 5. I'd have the absolute value of y is equal to 2. Now, what's going to happen is there's two possible outcomes that would have an absolute value of y being 2. That is when y is 2 or when y is negative 2. So we'd have points 7, 2 and 7, negative 2. And because of two outcomes for a single input, this is not a function. So this A is a function, B is not a function. You're accustomed to mostly seeing functions. When I look here, this is function notation. F of x is the outcome of the function, where x is the input. So if you were to see that f of 9 is equal to 4, that would imply that on a graph, you have an input of 9 and an outcome of 4. Because when you substitute in 9, out comes 4. The whole thing is valued at 4. In function notation, this x, this input, represents this x that's right here. If you have f of negative 3, what it means is we can replace the x in the function by negative 3. And so the square root of negative 3 plus 7, which is the square root of 4. The square root of 4 is 2. So f of negative 3 is 2. This g of x is just a different function being named. So if we look for g of negative 4, it means we replace in negative 4 we replace x with the negative 4. So we have negative 4 squared plus 4. Negative 4 squared is negative 4 times negative 4 is 16 plus 4, which is 20. So g of negative 4 is 20. Now there's a number of things that we can do with functions, one of which is right here. This here is talking about the sum of the two functions. This is the same thing as f of 2 plus g of 2. So we could go ahead and look at the square root of 2 plus 7 and then add it to 2 squared plus 4. This being f of 2, this being g of 2. So we have the square root of 9, which is 3, plus this being 4 plus 4. F plus g of 2 is the sum of the two functions. When the input is 2, it would be 11. If I'm going too fast, feel free to pause the video at any point in time. That's something that's within your control. Now, if we have f minus g of negative 6, what's going to happen here is that's the same as f of negative 6 minus g of negative 6. And what we would have here is we'd input negative 6 into f, so it would be a square root of negative 13 minus negative 6 squared plus 4. Because the square root of a negative number is not real, this does not exist. But if it was a number that did exist, for example, if it was the square root of positive 13, we could finish evaluating this, and our simplified version would be the answer. And here we have f divided by g of 0. That's the function f of x divided by g of x at 0. And I'm not loving this situation right now. I'm gonna change for these parts right here. I'm gonna make this the square root of x plus 7, and we're gonna do the rest of the parts with x plus 7. So please change that in your notebooks or your notes. I'm gonna go back and I'm gonna edit this to, if I had f of negative 6 now, it would be the square root of 1 plus negative 6 squared plus 4. So this would be 1 plus 36 plus 4, which would be 41. The do not exist happened when we had a square root of negative. However, I changed the problem, so now we would have the difference being the square root of 41. In this one, it would also make us now potentially have a real answer. F of 0 is when we input 0 as x, so we'd have the square root of 7 in the numerator. And g of 0 is when we input x being 0. So 0 squared plus 4 is 4. So this expression is the square root of 7 over 4. Now here we have the multiplication of the two functions at 2. So we have f of 2 times g of 2. So in here with f of 2 times g of 2, we would find what f of 2 is, which is the square root of 9, and multiply it by the g of 2, which is 4 plus 4, or 8. So we have 3 times 8, which would make this 24. Now down here, this is a function within a function. What's happening is we have f's input being g of the square root of 5. So we can first find g of the square root of 5 and then input that into f. G of the square root of 5, g of x is x squared plus 4. So we have the square root of 5, the input, being squared, plus 4. So the square root of 5 squared is 5, plus 4 is 9. So g of square root of 5 is 9. And then we can input the 9 into the f function. So this would then be the square root of 9 plus 7, or the square root of 16, which is 4. So the f of g of square root of 5 is 4. We could do the same thing for g of f of 8. That would mean that we're inputting the 8 into f first, and then the result, the outcome, we would input into g. So finding f of 8 first would give us the square root of 8 plus 7. This gives us that f of 8 is the square root of 15. So we're doing the g of the outcome of f of 8, which is the square root of 15. So that would give us the square root of 15 squared plus 4, because we're inputting the square root of 15 where the x is for g. So you'd have 15 plus 4, or 19. The last part we have here is what the g of f of x is, and the f of g of x. We also notate this as g of f of x, or over here we also notate this as f of g of x. Those are just different notations for the exact same thing. What they mean for both of them is that you input the f of x into the function g. So since g of x is x squared plus 4, we are going to input the f of x right in where the x is, square it, and then add 4. So g of f of x now has the entire function f of x as the input. And f of x as a function is the square root of x plus 7. So we're taking the square root of x plus 7 and squaring it, and that's going to give us x plus 7 plus 4. So g of f of x is x plus 11. And in this case here, we're going to do the same thing, but since f of x is the square root of x plus 7, we input the g of x into there. In the square root, we're going to take g of x and we're going to add 7 to it. Well, g of x is x squared plus 4. So f of g of x is the square root of x squared plus 11. Now, there's no additional simplifying that we can do with this. We can't distribute a square root. So this here is completed and simplified.